tell us about lattice, anomalies, and persistent order.
All right. Let me start by thanking the organizers for putting together such a nice workshop from a scientific perspective, as well as for finding such a beautiful place to hold it. It's been great fun, and I'm very honored that I'm able to give a talk. So I want to tell you about some projects that I've been doing with linear combinations of the folks on this slide. That's probably mostly based on some forthcoming work, as well as some work that's already appeared. So let me just dive in. Okay. So as I think everybody here knows, Lattice Monte Carlo is one of our most powerful tools for studying strongly coupled field theories, for example, QCD. Not the only one, but among the most powerful ones. But a challenge for lattice field theory, and Lattice Monte Carlo in particular, is that often quantum field theories of interest have some symmetries that are somehow involved in anomalies. So for example, QCD has close to massless quarks. So if you really want to understand the behavior of QCD with massless quarks, in that limit there's some interesting anomalies, and that's difficult to get right, as I'll review in just a second. Another really prominent example, which is actually way harder, is the standard model, right? In the standard model, the fermion fields have no mass terms. It's not possible to write fermion mass terms in the standard model. It is a chiral gauge theory. And so, I'm not entirely sure why you would really want to put the standard model on the lattice for practical reasons, but as a conceptual matter, we don't know how to do it because it's so hard to write down chiral gauge theories on the lattice because of anomalies. So basically what I'm hinting at is that there's an infamously difficult problem, which is how do you get field theories with anomalies onto a lattice, both for practical reasons and even conceptually. So why might this be hard? There are like many stories one can tell here, so I'm just going to pick one which is the easiest, but is not the most systematic. The one way to motivate the issue, the way a lot of textbooks hand-wave their way about it, is to say, if you think about continuum quantum field theories, and you pick the simplest type of anomaly, something that you can see from a triangle diagram, then the things like the ABJ anomaly appear to come from subtleties in regularizing one-loop diagrams. I mean, everybody here knows that's a misleading statement in practice, but they appear to come from subtleties in regularization. And on the lattice, there's no regularization in the first place. Or to the extent there is, it's like everything is regularized from step 0. And so naively, there shouldn't be any room for anomalies in the first place. That's a common statement you'll find in textbooks and maybe even some papers. Another thing that is tricky is typically anomalies somehow care about topology in field strings. Like instantons get involved in anomalies, that kind of stuff. And when you discretize a quantum field theory on the lattice, unless you do a lot of work, you typically do not respect field space topology. So for example, things like instanton numbers are typically not quantized in lattice field theory unless you really go to extreme lengths to get it to work. And that's hard to do. And indeed, the simplest example of things where anomalies appear is with fermions. And if you naively try to stick fermions in the lattice, people noticed basically instantly when they were first inventing lattice QCD in the 70s, people like Wilson, that you put fermions in the lattice in the most naive way, you immediately get fermion doubling. The anomalies cancel, but if they're physically interesting anomalies, they won't need to cancel. This is like ancient stuff that people have known for a long time. Okay. And in fact, the reason this is all pretty hard, in the particular example of fermions on the lattice, is not like a lack of cleverness on the part of lattice field theorists. Lattice field theorists are extremely clever. And the issue is there's a theorem that people proved also early in the subject, called the Nielsen-Mumia theorem, which basically lists a bunch of properties that you would want to have when you discretize a fermion, and then basically says you can't have it all. So how does it work? What the theorem is about is the Dirac operator. The Dirac operator is just gamma mu d mu. So you might want to discretize this thing. So replace the derivative by some type of difference operator. And the theorem says that you cannot maintain the following 4 properties all at once. One property is continuity in the momentum. That physically is something you might want because it basically tells you have locality. And normally locality is pretty sacred. Another thing that you might want is that for momenta which are small, in particular compared to the lattice spacing, you would want something that looks like the free fermion Dirac operator. That, if you don't get that, then It's not clear what you're doing, because you're trying to get a fermion. You want the Dirac operator to be invertible everywhere except at zero momentum. If it fails to be invertible somewhere else, that other point can be thought of as another Dirac fermion physically. That would mean some kind of doubling of fermions, or quadrupling or whatever. And the last thing is chiral symmetry. Okay? So if you're trying to get a chiral fermion in the lattice, meaning one with a zero mass, then the Dirac operator should commute with gamma 5. Sorry, anti-commute. So this theorem has been like a major roadblock that's motivated many discussions. Yeah, go ahead.
Very naive question.
Yes.
So in a theory that is strongly coupling the IR, like UCD, why should I expect condition 2, like at low momentum?
Good. You could think, so this is all for a free fermion, right? So what you might want to do is you might want to first, when you go to the lattice, you're discretizing the UV of the theory. And then it does whatever it's fated to do in the infrared. Right? So here you're trying to understand what is the property of the UV fermion. Then Monte Carlo will tell you what happens in the IR. But first you need to make sure that things are right near the UV. That's a great question. So 50 years of work have led to roughly 3 ways around this theorem. One is called Wilson fermions, another are called staggered fermions, and the last one is called overlap fermions, and depending on who's in this audience, maybe I should say domain wall fermions as well, but they're basically the same as overlap for my purposes. So each one of these things, which I won't describe because I don't need them for my talk, gives up on at least one of these properties, and in some cases you give up on multiple properties here. And then you just deal with it. Okay? So, yeah, like a lot of effort in the lattice community has focused on trying to get around this theorem in some way. But you know, there are very few ways that people have found. Like I said, it's about 3, maybe a little bit more, but not that many more. Okay? So that means that.
Sorry.
Go ahead.
The staggered fermions doesn't completely solve the problem.
No, it doesn't.
It just reduces the amount of doubling.
Yeah, so good. So staggered gets this right, this right, this right, and it fails that one. Because you have multiple places where the staggered fermion is not invertible. So you still have doublers, just not as many as before. Okay? Wilson fermions get this right, and they give up on these 2. Overlap fermions get this right, and they give up on these 2 as well, but in a more clever way. Okay, so, yeah. Good. There's another question? Yes?
Just continuity, you mean analyticity?
Yeah, analyticity. So if you look at the proof of the theorem, it's a topological proof, and it's strictly speaking basically only assumes continuity. But for locality, you actually do want analyticity. Yeah. But the Nielsen-Lemire theorem is really like a statement about continuity of momentum, not about analyticity, strictly speaking. Okay. People always say analyticity here, then I looked at the theorem, it's not correct. It's actually continuity. But, okay. Just, I can point you to the paper that, at least where I saw that. Okay. So there's so few ways around this that if you can come up with any new approach, it could be interesting. Even if it's in a slightly stupid situation, which you don't care about that much for physical reasons. So let's not be too ambitious, and let's consider maybe the simplest situation in which you can have interesting anomalies that involve fermions. And that would be 2-dimensional quantum field theories with Dirac fermions that are massless. And then we're going to think about coupling them to gauge fields later, and we're going to focus on abelian gauge fields. And extending to more than 2 dimensions and coupling to non-abelian gauge fields, we'll leave that for later. If we can already get this right in some new way, that would be interesting and maybe thought-provoking. And so a result that I'm going to mention is that it turns out that one can put such quantum field theories on the lattice, these particular ones, while preserving their symmetries and anomalies, with parallel symmetry acting just as in the continuum, by evading the Nielsen-Lemire theorem in a quite different way than the 3 things that I just mentioned. So I'll give you some sketch of how this works, but before getting into that, like the 2 things to keep in mind as you listen is 2 questions. Okay. First question, is it actually practical to simulate such lattice quantum field theories on a computer? Like, is it possible? Okay, because you might come up with something where you can write it down on a piece of paper and then you can never put it on a computer for practical reasons. That's one thing to keep in mind. And the second thing to keep in mind is you might hope that progress on this kind of stuff might lead to new theoretical insights that have nothing to do with putting this on a computer. If you're very lucky, that doesn't have to happen, but you might hope that something like that happens. So keep the second thing in mind as well. If I have time, I'll hopefully be able to say something about both. So to get motivated for seeing a way around the problem, let's remember the following thing. When people simulate QCD on the lattice, they don't actually put the fermions on the computer. What they do is they integrate them out on paper, and then they do a simulation. So here's a path integral with some fermions, some scalar fields, or bosonic fields more generally. I'm just being schematic. Phi just stands in for whatever bosonic fields you have. You integrate out the fermions, and if it's a direct fermion, you get the determinant of a Dirac operator. And, well, that's fine. But the thing to notice is that the Nielsen-Lemire theorem is a theorem about the Dirac operator. It's not directly a theorem about the determinant. Of course, in practice, to get the determinant, you normally need the Dirac operator, so this doesn't seem like a useful statement. But you might wonder, could it be that you could somehow directly discretize the determinant without ever discretizing the Dirac operator itself? Which sounds nuts. And for it to work, the only way that I can imagine it working is if you could find some expression for the determinant in the first place, which doesn't explicitly involve the Dirac operator, which is a tall order in general. But many of you probably know where I'm headed because you've seen a different version of this talk earlier, or maybe just because you know. In precisely two space-time dimensions, there's magic. So in two space-time dimensions, there's an exact duality called 2D bosonization that says that if I have a free Dirac fermion, and technical comment, if you gauge fermion parity, then that's equal to the compact boson compact boson quantum field theory. Okay? So here phi is a field, which is identified mod 2 pi, and r is some number that you have to pick so that you actually get the free Dirac fermion instead of something with a Thirring interaction. But okay, that's been known also since the 60s and 70s. So the basic idea that I will exploit in this talk is that what you could do is, you might want to think about this side. We're going to first bosonize. We're going to do a duality to a different theory, which in 2D is an exact duality. It's not some infrared duality. It's just exact. And then discretize. So we discretize this side. And, well, if we can do that while maintaining all of the symmetries, which is not completely trivial, and if we can do it without introducing some new disease along the way, which is also not completely trivial, as you'll see, then maybe we can benefit. And unfortunately, both of these things turn out to be true. So now let me go to the lattice. So in this talk, my lattices are going to be two-dimensional. I'm going to assume that they're square, although that's actually not necessary. I could work on a triangulation, but for simplicity, let's say it's a square lattice. It's anyway nicer. Sites are going to be S, links are L, plaquettes are P. There's also a dual lattice, and you can go from one to the other using the Hodge star. These are just technicalities. There's also like derivative operators on the lattice that you can set up in various ways. For a half-hour talk, I don't really have to say too much about this. So what I want to do now is I want to bring in the beginning of the idea that's going to help us, which is also pretty old. It's the Villain discretization of a scalar field. Again, dating back to the 70s. So let me try to explain it. It's received a resurgence of interest in recent years, for reasons you'll see in a second. So the Villain idea is if I have a compact scalar phi, it's compact, it's like defined mod 2 pi, that's what I mean. So when you go to the lattice, what you can do is you can represent this field phi in the continuum by two fields in the lattice, not one. One of them is just a real valued field, and the other one is a discrete field, which lives on links. And the idea is that you impose a discrete gauge redundancy by shifts of 2 pi, so that this real field phi shifts by 2 pi, and the field n shifts appropriately, so that, for example, d phi minus 2 pi n is gauge invariant. And what this does is it makes sure that physically what the combination of phi and n describe is a compact field. Okay? That's the beginning of the idea. So now, so what can you do with this? Well, you could, if you have a compact boson in a continuum, it's compact. So it could wind around some contour. And if there's a non-trivial winding number around some contour, that means in the middle of the contour somewhere there's a vortex. Right? That's a thing that can happen. So we can ask, how does that work on the lattice? Well, you can go and calculate the would-be conservation equation for the winding current. And by the way, if you think back to the fermionic theory, meaning the one with the Dirac fermion, the winding current here is actually the vector current of the fermionic theory. And the shift current for the scalar is the axial current in the fermionic theory. So when you compute this the lattice version of the divergence, or differential geometry version of divergence, and d squared is 0, the way I've set things up. So this part doesn't contribute. You just need to pick up something from the second term here. And, well, this divergence of the d mu, j mu winding, okay? It's not 0, it's dn. So it's the field strength of the Villain gauge field. And, well, n is an integer, so dn is an integer. So, so this side is some integer. So that immediately means that since that integer is not 0, then the winding current is not conserved. And physically, we can understand this by saying that when dn is not 0 on some plaquette, that means that there's a vortex sitting in the middle of that plaquette. And the field configurations sum over the insertions of all possible vortices, so that means that winding number can jump by any integer when you sum over them, and so you're dead. There's no winding symmetry. And the modified Villain idea, which I should say dates back to a paper by David Gross and Igor Klebanov and was sort of rediscovered and rephrased in the convenient language more recently, and people understood anomalies in this context and so on, is basically you could modify your Villain model from the 70s in a slight way so that dn is just 0. And if dn is 0, then this side is 0 and you're safe. So how do you do that? What you can do is you can add a Lagrange multiplier field theta, which only appears in this second term here. And if you sum over theta, that sets dn to 0 in every plaquette. So that gives you a winding symmetry. And you also have a shift symmetry. So if you turn on a gauge field for the shift symmetry, which is to say the axial symmetry, it should be the case that the winding current is no longer conserved. And you could quickly go through this with the lattice action that I wrote for you, and you discover that indeed it's not conserved. And not only is it not conserved, but it's equal to basically the instanton number, which is exactly what you expect. Okay? This is precisely the 't Hooft or ABJ anomaly for U1v times U1a for Dirac fermion. So this gives you confidence that this lattice theory that I'm showing you is a good discretization of a Dirac fermion. Of course, it's just a free Dirac fermion for now, so not that exciting. But I should say that this is not so easy to get. I mean, if you really just started with the fermionic theory, I don't know how to do this. In particular, this is nothing like overlap fermions. Chiral symmetry acts locally. So this is somehow better than that. But there's a scary thing. Okay, so you look at this thing, and there's an I in the action. So that means the Euclidean action is complex, and so there's a sign problem. And sign problems are really, really bad. Like, they're really bad. So if your Euclidean action is complex, okay, and you're giving a talk with lattice people in the audience, then immediately people start throwing tomatoes at you if they were being frank. Because, it means that e to the minus s is not positive, which means that e to the minus s doesn't define a probability distribution, which immediately means you cannot do importance sampling Monte Carlo, and you have to do a high-dimensional integral. The only reason we can do high-dimensional integrals in Monte Carlo is because of importance sampling, which relies on e to the minus s being a probability distribution. That's a disaster. Not only that, but physical answers now depend on extremely precise cancellations between complex contributions. So on its face, there's a sign problem here, and you could never hope to put this in the computer unless you solve it somehow. And the good news, and the reason that I'm giving this talk, is that this particular sign problem is easy to solve. The reason it's easy to solve is that summing over theta, we know what it does. It just gives you a constraint. The dn is 0. But that's such a simple constraint, you can just solve it when doing proposals for your updates for your field configurations during the Monte Carlo. And provided that your updates don't violate the constraint, which, like I said, is easy to do, the imaginary term can be dropped, because it never contributes. So let's make sure that this really works, okay? And that we can simulate this type of model.
Sorry, can you
please, yeah.
Can you go back to the previous slide? So if the last term is just the Lagrange multiplier, can you not just drop the I and then? That's
exactly the idea, but then having done that, you have to make sure that when you update your field, you have to respect the constraint. So you can do that. So that's absolutely right. So a random imaginary term does not take the form of a simple constraint. in which case we usually don't know how to resolve the problem. But what I'm trying to say is that this sign problem is actually innocuous. It looks scary at first, and it's actually harmless.
Yes. Do you have problems with the ergodicity of the algorithm in this?
No, you can easily show this without it.
Okay.
So let's see how much time I have to actually say.
So it means you update, and if it doesn't satisfy the constraint, you throw it away and try again.
That's one way, or you could just make sure that your updates just respect the constraint. There's like worm algorithms will do it, for example. So that's the thing that we do that turns out to be efficient. But there are simpler things to do too. They're just not very efficient. So you can just make sure that your updates respect the constraint.
But you could just throw them away.
You could just throw them away. That would just be a little bit inefficient. So it's better to find a way to propose updates that automatically satisfy the constraint while being ergodic. So you have to prove that. But
Yes. You calculate the autocorrelation time? Or?
yes.
Okay.
So
And that behaves well.
good. It depends on the algorithm, the precise algorithm. We have many algorithms that we've tried, but we found several that have mild autocorrelation times. So fairly big lattices, like 30 by 30 lattices, the autocorrelation time, like at worst, around 35 or something, and you want to count those steps, so it's really not so bad.
On 2D lattices, there is a way to explicitly solve the constraint. Basically, Nij is Mi minus Mj plus some.
You could do that here too. So you could explicitly solve it. Good.
Yeah.
So you can explicitly solve the constraint that
It's
way.
like a locally pure gauge, but there
Good.
can
That's
be
right.
winding.
That's exactly right. That's the first thing that we thought of. That works. We did simulations with it. The problem is it has large autocorrelation times in big boxes. And then we had to find a different algorithm that doesn't have the same issue. And then
That's actually what David and I did. We didn't have the Lagrange multiplier.
Yeah.
We just explicitly.
Excellent. So that's also the first thing that we tried, but then ended up, for practical reasons, doing something more complicated. But okay. So I want to tell you, probably all I'll tell you today is about a warm-up problem, and then I'll tell you where I'm going with it. Okay. So the warm-up problem is the following. So instead of removing all vortices, let's just remove some of them, just to see what happens. Okay? So how do we do that? Well, we want to have what the constraint looks like. So instead of, in the previous slides, sticking a real value of Lagrange multiplier, theta, which if you integrate over just removes all vortices, you could stick an integer valued field v and put some parameter w, which is an integer, and the way this is set up is integrating over v makes the path integral 0, so it gives a constraint, unless dn is 0 mod w. So if w is 5, you remove vortices with winding 1, 2, 3, 4, but keep the ones with 5, then keep the ones with 10, keep the ones with 15, keep the ones with minus 5. That's the idea. So you remove a bunch of vortices, but not all. Okay. So of course, if w goes to infinity, we're just back to where we started. But kind of a fun little toy problem to think about. So if there are no vortices removed, so w is 1, we haven't done anything, this extra term is just trivial, then you expect a BKT phase transition at some order 1 value of the Hoffman parameter here. The reason is that, if kappa is very, very large, you expect to land on some kind of compact boson CFT, but there are vortices, so if they proliferate on you, they're going to drive a mass gap. That's the BKT mechanism. So that's been known for ages. Well, if you increase W, you're removing some vortices. So as you remove more and more and more vortices, you should expect that the BKT transition gets pushed to higher and higher kappa. Seems like a very natural expectation. In fact, you can wave your hands a bit, try to figure out, well, how should it scale with W, and this is the answer. In fact, you can do better than that. You can prove that this is how it behaves and get the number in front, right? I won't tell you about that, but so we know analytically what to expect, but never mind that. So the thing that I want to highlight is there's something interesting here compared to a typical situation, which is that there is a mixed 't Hooft anomaly between the shift symmetry of phi and the winding symmetry. It's inherited from the 't Hooft anomaly between the winding and shift symmetries in the model I told you about earlier. So that means that your choices for the ground state, as you vary kappa, is that you either land on some conformal field theory, which is what it's going to do if it wants to spontaneously break U1, but it can't because you're in 2D. Okay? Or you're going to land on a state with a spontaneously broken winding symmetry. But a trivial gapped ground state is simply impossible because of the anomaly. You cannot match the anomaly with a trivial gapped ground state. And That's as a function of kappa viewed as a parameter in the action. If you view the lattice as a spatial lattice, then kappa can be interpreted as an inverse temperature. That would be very common in the condensed matter literature. And what these statements would mean is that thermal fluctuations cannot fully disorder this particular system, which is quite unusual. And it's an example of something called persistent order, which condensed matter people really are excited about. This is like a baby example of that. So what we expect as a picture is the following. Okay, so here's W, you increase W. Here's kappa. So when W is 1, you didn't do anything. This is the picture that you would find in textbooks about BKT phase transitions. And you increase W, and it gets pushed to, the critical value of kappa gets smaller and smaller and smaller and smaller and smaller, and over here you get spontaneous breaking of a winding symmetry. That's what we expect. And of course, as I mentioned, on the gapless side, you know where you're supposed to land physically. You're supposed to land in a 2D compact scalar CFT. In that compact scalar CFT, there are vortex operators. They're charged under the U1 vortex symmetry of the CFT, but the U1 vortex symmetry is not a symmetry of our UV theory, our lattice theory. There we only have the ZW symmetry. And so vortices could proliferate, in principle. And if they ever go relevant, you develop a gap. And you can even figure out what is the critical scaling dimension of various operators at the point where you have this phase transition. So this is very old stuff, like people have known this again since the 70s. But I'm not so sure people have explored so much the situation where you constrain the vortex sum. Maybe somebody did, but I couldn't find it. Okay, so we know various scaling dimensions at the transition. And so we can take advantage of that in finding nice quantities to track to find the phase transitions. Okay. So for example, you could look at the two-point function of the spin operator. That's condensed matter language for thinking about the two-point function of e to the I phi. That's what S is here. You know how it scales at the transition. Or you could define some susceptibility, which is like the integral of that over space. And that's a nice thing to do, as it turns out, for W less than 3. And not so good if W is bigger than that, but that's fine. And if you normalize either this thing or this thing by its expected large box or large separation behavior, and plot it as plot it against the volume or the separation, then if you define things correctly, basically you should have a function that goes flat at the phase transition. So this is what we should expect. I'll actually show you a picture with data in a second. I wanted to show you a picture without any confusing error bars on it. Just like, what should you expect, okay? So you plot, you have an n by n lattice, so that's my proxy for size. And then 1 over n goes this way, so this is larger and larger volumes. And this is like the log of some susceptibility that's normalized in such a way that at the critical coupling, that's the black points, it should go flat. If you're above the critical coupling, it will actually grow with volume. If it's below the critical coupling, it should decrease with volume. Okay, so we're going to have pictures of this with actual data in a second. I'm running out of time, so that's fine. So we have to do Monte Carlo. Conceptually, Monte Carlo is extremely easy. You just generate independent field configurations. And on those configurations, evaluate your observables. And then the error goes like 1 over the number of independent field configurations. In principle, that's all. At the beginning of this project, that's about all I knew about Monte Carlo. But I have collaborators who tell me better. It's all much more difficult than it sounds because, one, we have this sign problem naively, so you have to deal with it. Second, as people already mentioned, there could be divergent autocorrelation times. So one field configuration and another one which occurs like 1,000 update states after could actually be very closely correlated. And that would be very bad because they're not independent. Yeah, that's a problem potentially. Also, some observables that we're interested in are actually only really defined as defect operators, like vortex operators. And then you have to find an efficient way to study them. And all these problems can actually be solved, at least in this particular example. So you can generate configurations that just satisfy the constraint. There are algorithms that do that have smaller correlation times, and there are even algorithms that can compute defect operator correlators quite efficiently. That took us the longest to figure out, actually. But so, well, I said on this slide I'm going to tell you about one such algorithm. I'm just going to very quickly show a slide where I tell you the idea, and then won't tell you any technical details live. You can ask me one-on-one if you really want to know how it works. So here's an example of an algorithm that actually works. So works meaning it's efficient and everything. So you start with a configuration where dn is 0 everywhere, and you do whatever you want with phi. Or maybe phi is 0 everywhere at the very beginning. Okay? It's not going to stay that way, okay, but that's how you start. Then you first generate a new configuration for the ends that actually satisfies dn equals to 0, which is not the thing you want, but just do that first, using a worm algorithm. Worm algorithms are like exactly what you want to update integer valued fields that have to form closed loops. So if you don't know about worm algorithms, that statement might be helpful. If you don't, this is mysterious, but that turns out to be true. Then you sweep through the lattice, and you also have that phi field. So you update the phi field. You propose updates for the phi field, and you accept and reject them using a metropolis accept-reject step to make sure that you have detailed balance. By the way, when you do the worm thing, you're also using metropolis accept-reject at the steps as you grow the worm and so on. So it's also satisfying detailed balance. But this is not satisfying the constraint we want yet. So the next thing you do is you sweep through the links, and you propose updates on the links that are like link plus w times some integer, like plus or minus 1. That amounts to going through the lattice and proposing an update where I stick a vertex somewhere, the allowed vertex. And again, you accept reject using metropolis.
What's W?
W is in my constraint. My actual constraint is that dn is 0 mod w. So this gets the 0. This is the mod w.
Well, W is empty.
And w is some integer that I pick once and for all.
But you're going to then take it to infinity?
Yeah, you could eventually take it to infinity. So w is just, bear with me here, it's just this thing that I can just choose.
But you really want infinity.
Infinity is actually easier. Then you don't need this last step at all. That's even better. So infinity is easier. So if you want to do the infinite w, you just don't do this step. This step puts in the possible vortices. Okay, but if you don't do this step, you already got the w equals to infinity. Then there should be no BKT transition at all. You can see that actually, numerically. So you can prove that this algorithm, as well as cousins of it that have some other features that are nice, it's ergodic, it satisfies detailed balance. It's also not a local update algorithm because of this first step. Now, a priori, you don't know if any given amount of a non-locality in your update algorithms is enough to mitigate autocorrelations. There's an experimental question you have to check. That's good enough. As it turns out, for anything that we've done so far, it's good enough. I'm going to skip how the one works. So I'm going to show you some results. So for w equals 1, this is reproducing ancient stuff. People already did this long ago, although not using this particular algorithm. So there's no constraints on the vortices. And there's old literature, for example, Duru, Yankee, and Nather, but it even goes back to like, Kosterlitz. Kosterlitz also predicted this value for the critical coupling. So what you should be seeing here is there's one particular color, basically the red one, that is basically pretty flat. So that red one is a kappa of around 0.8. So within our error, this is, I'm not trying to show you like production results, it's like some preliminary scan. This is around kappa of 0.75. We can do much better, we have much better results by now, but yeah, just to give you an idea. So you can basically see that if kappa is significantly bigger than the critical value, then it starts growing. If it's smaller, it falls. But right around the critical value, between 7 and 8, it's trying to go flat as you increase the volume of the world. That's exactly what you should expect to see. Well, w equals 2 is like relatively new. Okay, so you could put that in, and again, this is preliminary, but what you expect is a kappa of 0.185. It's smaller. That's the critical kappa, at which you have the BKT phase transition. And you do a parameter set again, and somewhere around this purplish thing, around 0.17, but this purple here, this one, is 0.18. Sorry, I missed. So that's again in the right ballpark. So you could add extra numerical resources, and you can do much better. So you can get basically this 0.185. So this is giving us confidence that we understand what's going on, that we have algorithms that are efficient, and we can compute vortex correlators and show that on the other side of the BKT phase transition, the gapped side, there are degenerate ground states, and so on. So I'm not showing you high precision results yet with the error bars and the critical coupling. We're about to start our production runs. We spent ages being stuck on how to compute vortex corollaries efficiently. It's subtle, like I said, because they're defect operators. But we just sorted it out recently, and so now we can just fire the computer and do it. And by the way, firing the computer, to give you some idea, like these points over here, this is like laptop for about 30 minutes. So we're not talking particularly significant numerical resources. Okay. So I think this warm-up example is a little bit amusing on its own. But the same technology can be used to attack much more interesting problems. But I don't really have time to tell you much about it. Let me try to see how I can say the last thing that I wanted to say in like.
It can take 5 minutes.
5 minutes? Okay. Let me see what I can do. So let me just target application that I think is really trivial is a chiral gauge theory. So there's simple chiral gauges in 2D which are abelian. So here's an example of one. You take two left-handed Weyl fermions with charges 3 and 4, and two right-handed Weyl fermions with charges 5 and 0, and couple them to a gauge field with those charges. That's a chiral gauge theory. It's called a 3-4-5-0 model. And putting chiral gauges into lattice is like among the hardest things that you can do in lattice field theory. It's very difficult. There are not so many known ways. And you can handle it by the tricks that I told you about. So 2 questions you can ask. Does it even work? And second, do you learn anything new? And so the action is a bit hairy. I'm not going to talk about it. But one thing you can do immediately is make sure that when you do a gauge variation, it's gauge invariant. And you do the gauge variation, and it doesn't look gauge invariant. This is the gauge variation. But this vanishes when this combination of charges vanishes. These are the charges, vector and axial charges of the 2 Dirac fermions you can build out of the Weyls. Well, and this quantity is supposed to vanish precisely when the gauge anomalies cancel. This is good. This is the first idiot check when you do a chiral gauge theory. It better only work when you satisfy anomaly cancellation. It does. You can also, I'm not showing it here, but you can also verify that the 't Hooft anomalies of this model, global symmetries, are also correctly reproduced in the lattice. And that gives us confidence this is the right theory. But then you can take this horrible looking thing that I showed you a minute ago, and you can integrate out the gauge field, and then simplify as much as you can. This is actually quite annoying. It sounds very simple to say, but actually doing it was annoying. And you land on something that looks a lot simpler. So what it looks like is 2 scalar fields, okay, and some kind of like mass term or something that mixes them, and then some discrete stuff with some Lagrange multipliers. So here phi is some gauge invariant combination of the axially charged fields, and rho is some gauge invariant linear combination of the vector charged fields. And what you can see is one combination is gap, the other one is gapless. That's exactly what you expect to match the 't Hooft anomaly. So that's reassuring. Next, you notice that this term gives a constraint that dV is 0. Sigma is some real field. So it's a Lagrange multiplier field. So this first term is harmless as long as you propose updates where dV is 0. Second term at first glance looks extremely alarming. There's an I in it, and I haven't told you what F is, but it's just some function that relates a link. It connects fields that live on different links, okay? So there's some technical details I'm sweeping under the rug in view of time. And a very non-trivial fact, which is traced back to some identity involving cup products, is that when dV is 0, the second term is also automatic. That can be shown analytically, although it took us a while to notice. So in practice, there's this one problem. You make sure this one's right, that one goes away back, like automatically. I'm not saying that's obvious at all. Okay? That was not obvious to us. We thought that in this model, there would be a horrific sign problem, but just happens not to be.
But does it mean that the term can be just dropped whatsoever? Because
it can be dropped as long as dV is 0.
yeah, so if you're doing updates, which...
Exactly, so you can just drop it, yeah. If you start calculating defect correlators, then depending on exactly how you do it, you might have problems, but I think there are ways to handle it. Well, that's some technicality. What I want to come back to is, I told you, like, you would hope that finding a new way to put a theory in the lattice gives you more than just the ability to do Monte Carlo, but tells you something you didn't know already. And here, well, it's a little hard to handle. The literature is very big, so maybe somebody noticed this, but we haven't found it yet. So you take this model, and you just stare at it, and you notice that if kappa happens to be 1 over 4 pi, something happens. So before I tell you what happens, what is scanning kappa supposed to mean? Varying values of kappa, if you trace back through Bosonization, step by step by step, it's varying Thiering couplings for the fermions. So somewhere in the Thiering coupling space, something interesting happens. You set kappa to 1 over 4 pi, and you see an extra Z2 symmetry, which exchanges phi with rho. And if you translate phi and rho back to the fermions, you see that this is a bizarre symmetry. See, e to the I phi, which is a gauge invariant thing, back in terms of my original bosonized fields, is this, then you trace back, and it's some weird 6 fermion operator. Okay, like whatever. E to the I rho is much weirder. It's some fermion bilinear times something you can't even write in terms of the psi field, some disorder operator. So the symmetry exchanges something with a disorder operator with something that is built out of normal fields. It's weird. In the bosonic theory, because it's some duality, right? This could be something that you can see in the level of the action, but in the original fermionic theory, good luck with that. And as far as I know, this just happens not to have been noticed before. So this
depends on the specific charges you introduced originally?
Yeah.
And how did you choose those?
There is like the first
Were you
thing.
lucky enough to find?
Good. Sorry, yeah, so if you go back to this step here, this is basically the first abelian chiral gauge theory everybody talks about in 2D. They're like, it's like the simplest one. It's the one about which there are like 300 papers, and then the rest have many fewer papers. It's like the simplest example that everybody tries their method on.
And if you look at the more complicated ones,
yeah,
would you find the same symmetries? New symmetries?
That's a great question. We're trying to figure this out now. I swept some things under the rug, as you could probably guess. So this magic that these imaginary terms can just be dropped, it happens for some other examples of chiral gauge theories, but not in all of them, even the abelian case. And we don't know whether that's because we haven't been clever enough to write it in a nice enough way, or whether that's a deep statement.
Like when it happens, you have this new Z2 symmetry?
And for the Z2 symmetry, we don't know, because the thing, we're not even sure. So we found a simple looking action in which we could check this easily for the particular case of 3450. And in the other cases, even the sign problem disappearing is difficult. Yeah. And the action looks much more.
So you don't know.
So we don't know yet. So it's something that Evan and Theo and I are trying to sort out.
But if you just care about the symmetry, you're not putting the system.
Well, the thing, yeah. So
no, but the sign problem might just be for this particular example.
Yeah, I mean, if you just care about the symmetry, so I think that you could carry out these steps in the continuum too, to be honest. So that's something that I should do. I haven't done it. And I think if you did this in the continuum, you would have noticed this. And it wouldn't shock me if in the huge literature on this topic somebody has noticed it. I just haven't found anybody. I give this talk many times now, this part of it. Nobody tells me, oh, I knew that. So maybe that's because they don't care, or maybe they didn't notice it. I don't know. I had condensed matter theorists tell me, oh, we knew that. Then further discussion showed, no, they didn't. So anyway, so the point that I want to make here is that this is our next target. This can be simulated. We haven't done it yet, but it'd be fun to play with it. I'm not going to say that. So let me summarize and shut up. So there are simple lattice models that have anomalies. They have persistent order. They can be studied using Monte Carlo. And if you generalize them a little bit, coupled to gauge fields, you can study many interesting field theories.
What would be, can you be more precise what persistent order is?
Oh, it's just that as you vary parameters, you never land on a trivial gap phase. It's just anomaly matching. Yeah, it's nothing very sophisticated. So with that, I'm done. Sorry for going over time.
This is very two-dimensional, right? You use for personalization.
That's right. As it stands, it's very tight to 2 dimensions. So with Maria, who's in the audience, and also with my postdoc Shi Chen, we're trying to go to 3D and maybe to 4D with the following idea. You start in, so I don't know how to do bosonization in a useful way in 3D and 4D. That's not a good starting point. But what you can do is you can take a 3-dimensional theory and do something that the condensed matter people would call a coupled wire construction. Okay, so what's the high energy way of saying it? You compactify the theory in a circle and discretize on the circle. If you don't want to introduce any extra stuff, you use staggered. If it's one direction that's discretized, staggered fermions don't produce any doubling. What you get is a two-dimensional quantum field theory, just with n different fermion fields. And that can be bosonized, and then discretized. Then you could try to run the same idea for 4D. The challenge is, do this and do it correctly while getting all the global structure right and getting the anomalies right. That's what we're struggling with now. Jury's out. I suspect that it has to work, but we haven't finished. The thing that I really don't have any idea about is how do you do non-abelian gauge fields? Because I don't know, even in 2D, because to my knowledge, nobody has come up with some way of discretizing the Wess-Zumino-Witten model, which is the bosonization of multiple fermions with a flavor symmetry, in a way that preserves the symmetries of the Wess-Zumino-Witten model. And the reason for that can be traced to the fact that the Wess-Zumino-Witten model has the Wess-Zumino-Witten term, which is quantized, and nobody knows how to preserve that quantization on the lattice.
So we need Finland for that.
You need some analog of Villan for that, and it has not appeared just yet. So we have some extremely tentative idea for something that maybe perhaps would work, but I kind of doubt that it's going to work. We're trying something, but if you got me drunk and asked me, I would tell you it's not going to work.
Can you do 3D? Helping Wess-Zumino writing in 3 dimensions? Wess-Zumino Witten term.
Domain wall,
Yeah, you could try domain wall things, but then the thing that you should start with is the Chern-Simons theory in 3D or something, a non-abelian Chern-Simons theory. And that I also don't know how to do. Even the abelian 3D Chern-Simons theory was only recently constructed on the lattice in a fully systematic way by Theo, who's one of my collaborators and one of his friends. So that's its own very interesting story, which is not my story to tell. But there's not a construction yet for the non-abelian case.
Actually, just a comment. So one thing I do hear ConMat people talking a lot about is the 3D version of this where you only retain monopoles of charge to
Oh yeah, you could do that. You could do that. In fact, when I first started thinking about all this, that was my motivation.
Mm-hmm.
I didn't immediately realize that this is a way of doing kernel fermions in lower dimensions. I wanted to do 3D gauge theories with the constraint on the instanton sum, or the monopole sum.
Yeah.
You could totally do it, and from our new numerics, I suspect you could do it still on a laptop. We just haven't done it.
But, I would think that someone talked about restricting vortex numbers, but I don't.
There's not, to my knowledge, there is not a Monte Carlo study of that. So the only person I could imagine who would have done it using this kind of technology is Tin, Suleiman Pasic and his friends, and I don't think they did it yet.
I just got a little lost how we were simulating the det of this Dirac operator. That's just the partition function of this boson?
That's exactly right, yeah.
So you try it for mini samples of the background gauge field and get some expression.
Yeah, that's right. So basically you trade d phi, so dA, that d of A, with e to the minus action of A. So you rewrite this as dA, d, like this dual scalar, and then some action which involves A and phi. And now you sample from this guy. And that amounts to sampling from that guy.
Got it, thanks.
And for whatever it's worth, if you're curious about playing with this numerically, we're writing an open source Python package that you could just use on a laptop. It's going to appear on GitHub very soon. And it will be completely open. Yeah?
That's one question. For your algorithm, you basically change each link by double, so that it always...
Yeah, that's the step that puts in vortices of the appropriate winding, yeah.
But can you not have vortices of appropriate winding if you change one link by not something which is W and another link at the same time? I mean, for example, you could have...
So the constraint is imposed plaquette by plaquette. In fact, the constraint that follows from the Lagrange multiplier is separately valid at each.
For example, you could have +1 on the horizontal and -1 on the vertical.
Yeah. So that is taken into account. So so you could have if you have an update which is accepted, which produces something with W here, At the next step, you could produce something with W there or something.
What I mean is you can have a global change of all links and still you satisfy.
So if you have a global change of all links, I'm not sure exactly what you have in mind, but for example, winding configuration is taken into account automatically in this algorithm. So winding around the space-time torus, I mean.
Okay. Sorry, I meant, for example, if you change all horizontals to +1 and all verticals to -1.
Yeah, that's taken into account here. That satisfies the constraint automatic. That configuration satisfies.
I think the gauge transformation on link Mij is just Mi minus Mj, where Mi is an integer living on site I and Mj. It's like an z-valued gauge field, integer-valued gauge field, and the gauge transformation is a Boolean. You can just keep performing this gauge transformation.
So it's going to end up taking these into account. We can actually see them in our simulation. We actually monitor to see if we get those, and that sometimes sets our longest autocorrelation time, whether you produce these winding configurations. But you do, eventually. Yeah, it's a great question. We worried about it, but it actually works.
Yeah, let's thank Aleksey again.